Chapter 2, Part 4, Lewis acids and bases and relative basicity. The Lewis acid and base definition is that a base is an electron donor and an acid is an electron acceptor. Now, this seems like it's not at all related to Bronsted-Lowry, but in fact, this is very much related, and the two go hand in hand. So let's look at some examples. What's nice about this one is that this does not limit us to acid-base reactions that involve the transfer of protons, because believe it or not all acid and base transactions involve the transfer of protons. There are acid and base reactions that simply involve an electron donor and electron acceptor. So in this example, we have a base that has a lone pair and a negative charge, and we have an acid that can act as an electron acceptor. And what's going to happen is the lone pair is going to attack the acid. That is that lone pair making a bond to that compound being represented by the letter A. And this gives us a Lewis acid, Lewis base complex. Where we have a bond between A and B, and A is likely to be negative at this point. So this is a Lewis acid, Lewis base complex. Now, there is one really important Lewis acid that you're already familiar with, and that is the proton. So this proton transfer process that we've talked a lot about this chapter does fit in with the Lewis acid, Lewis base definition, because even as we're talking about the donation and acceptance of protons, what we're actually showing is electrons doing all the work. Chemistry always starts with the electrons, even when the electrons are not what we think we're moving. So in order for an acid to donate a proton, it's actually the base that has to kick that off by attacking the proton. So in this example, we have hydrochloric acid, which will act as our acid. We have water, which will act as our base. And we've seen this reaction before. The water is going to attack the proton, and that's going to cause the bond between hydrogen and chlorine to break. So even though we're talking about the transfer of a proton here, it's the electrons doing the work, and the Lewis acid and base definition explains that much more clearly than the Bronsted-Lowry definition does. So the base is acting as an electron donor. It's donating electrons to form a new bond here. And the acid is acting as an electron acceptor because the electrons are coming to it. And this is what allows a base to act as a proton thief and the acid to act as a proton donor. And then we end up with our conjugate base that has that extra lone pair. So when we're talking about relative base strength, there are kind of two ways that you could look at this. You could look at this as a comparison using pKb, but that would require you to learn an entirely new series of values. If we just think about relative pKa's, we can actually get just as far, and you don't have to learn anything new. This is a pretty basic chart that gives you an idea of common weak bases and common strong bases. So you can see I have all of the halogen bases here, all of our conjugate bases of strong acids down here listed as very weak, right? And then in the next one, we have water, alcohols, and ethers. We haven't learned these words yet, but we will soon. This is an alcohol and this is an ether. These are all weak bases. Now notice that all of our weak bases here with the oxygens are neutral. They do not have any charges on them, but they do still have lone pairs, so they can act as bases. These will all work as bases as long as you have a much stronger acid, like hydrochloric acid, hydrobromic acid. Next, we have ammonia and amines. This is starting to move in the direction of strong. And then we have hydroxide ions and alkoxide ions. These are the conjugate bases of the items that are one column over. This doesn't have a conjugate base, that's why you don't see one listed. So what we've done is we've taken off the proton, which is going to make this a much, much stronger base. And then we can see that same pattern on the next column. If you take a proton off of ammonia to make azonide, you're going to have a much stronger base. If you deprotonate an amine, again, strong base. And then this one doesn't have a conjugate base. So that's what this pattern is here. Now, how can we use pKa's to figure this out? When you're talking about pKa's, you have to be thinking about the conjugate acid of any of these. So we're not talking about the pKa's of these. These compounds don't really have pKa's. These protons would never ever come off. But the the conjugate acid of azonide is NH3. And we know the pKa of that. It's 38. So this is the conjugate base of something that had a pKa of 38. And these are all going to be in the same vicinity of about 35-ish. And hydroxide is the conjugate base of water. We know that the pKa of water is 15.7. And the conjugate base of methanol, the pKa of methanol is going to be roughly 16. I don't have that number off the top of my head. So we're using these numbers. Now we have to look at the conjugate acids of some of these amines. We actually saw the conjugate acid of ammonia earlier. It was ammonium. Whoops, sorry. That's NH4 plus. Oh, my pen is being glitchy. There we go. And I believe that pKa was around 9.25. The pKa, the conjugate acid of water is H3O plus, that's hydronium. And the pKa of that, I believe, is negative 1.7-ish. And then we get to our halogen acids. I don't remember the pKa's of all of these, but I do remember that the hydroiodic acid had a pKa of -9. So if we look at these pKa's, we can see we have our strongest acids down here and our weakest acids on the other side. So you can use pKa to determine relative basicity as long as you look at the conjugate acid of the bases you're comparing. You can also kind of memorize this table, memorize the order of this table. That would be a helpful thing anyway.